Testing 1, 2. Testing. All right, let's get some music on there. There we go. All right. Okay. So today I will be working on a coding game puzzle, an interesting one, probably a little harder than the ones I've solved in the past few weeks. It is called Skynet Revolution Episode 1. Ooh, exciting stuff. So your virus has caused the backdoor to open the Skynet network, enabling you to send new instructions in real time. You decide to take action by stopping Skynet from communicating on its own internal network. Skynet's network is divided into several smaller networks. In each subnetwork is a Skynet agent tasked with transferring information by moving from node to node along links and accessing gateways leading to other subnetworks. Your mission is to reprogram the virus so it will sever links in such a way that the Skynet agent is unable to access another subnetwork, thus preventing information concerning the presence of our virus to reach Skynet's central hub. Yeah. Okay. Rules. For each test, you are given a map of the network. Right. So, and it did say in the description that we were going to have to use graphs and probably the BFS algorithm, the breadth first search algorithm, which I have implemented in the past, but it's probably been over 2 years since I've used it. So this should be fun. The position of the exit gateways. Okay, hold on. We're good. Map of the network. Right, so that's probably the nodes and the links between the nodes. The position of the exit gateways. Right, the starting position of the Skynet agent. Evil gateway. Okay. So we're trying to prevent the Skynet agent to get to a gateway. Right, Skynet agent tasked with transferring by moving from node to node along links and accessing gateways. Right. Nodes can only be connected to up to a single gateway. Up to a single gateway. Right, so that makes things a little easier, possibly. Right. Yeah, it does. Each game turn, first off, you sever one of the given links in the network. Then, the Skynet agent moves from one node to another accessible node. And that's your one turn, and so on and so forth. Okay. Victory conditions, the Skynet agent cannot reach an exit gateway. Okay. Those conditions, the Skynet agent has reached a gateway. Simple enough. Simple enough. Okay, here's our input. Initialization input. So that's what we're being given at the beginning. Text representation of the network used in this example. There are 4 nodes, 4 links, and 1 gateway. Okay, so the first line gives us 4 nodes, 4 links, 1 gateway. The next 4 lines describe the links. So that would, yeah, this would be node 0 is connected to node 1, node 0 is connected to node 2, node 1 is connected to node 3, node 2 is connected to node 3. And what's this here? The last integer is the index of the exit code. So the index, they probably mean the node at which the exit node, a gateway, is what they mean. Yeah, okay. And there's only 1 in this one. So I'm guessing that if there was more than 1 gateway, you'd have more lines with indexes. So okay, this is what it looks like. Simple turns. Skynet agent starts at node 0. Okay? Represented as SI, I'm guessing for Skynet agent. No? SI, I don't know. Whatever. Skynet SI index, Skynet agent index maybe. Anyways. So our virus cut the link between the nodes 1 and 3. Okay, so we're being given every turn we're being given the position of the Skynet agent. Then we get to choose which link we sever. Say we sever this one here. Cool. Right. The Skynet agent moves to node 2. Our virus cuts the link between the nodes 2 and 3 here. The Skynet agent has been cut off from the exit. You have won. Okay. The tests provided are similar to the validation tests used to compute the final score, but remain different. Aha, yes, okay. So that means that once we're done passing all the test cases and we hit submit, it's going to go through another scenario. And that's to prevent hard coding stuff. And oh. That's weird. Usually there's a little button here to actually see the inputs, and oh, so maybe the way the Skynet agent moves is random, or maybe not random, but maybe its starting position is random, or maybe because otherwise why wouldn't? Well. It's true that if the thing moves around, our test cases would have to implement whatever the Skynet agent moving algorithm is. That gets pretty complicated. So it's going to be hard to locally test this this puzzle here. Okay. And by locally, I mean on my machine. Okay, so game input. The program must first read the initialization data from standard input. And we're being given a kind of a starter code here. Then within an infinite loop, read the data from the standard input related to the current state of Skynet agent and provide to the standard output the next instruction. Right, okay, so we've been through this already. That's the initialization input. Input for one game turn. Okay, so each turn we get one line. And the only thing we're getting as information is the position of the Skynet agent. Okay. Output for one game turn. That's what we have to give the system. A single line comprised of two integers, C1 and C2. Separated by a space. C1 and C2 are the indices of the nodes you wish to sever the link between. Alright, simple enough. 2 is, okay, so n is smaller or equal to 2, n being the total number of nodes. N is no bigger than 500, so that's not that bad. We shouldn't have to worry too much about performance then. L is the number of links in the level. So a minimum of 1, a maximum of 1,000. So really, again, not that bad. Basically means that on average, not on average, but yeah, as a maximum, full graph of 500 nodes, each node won't have more than 2 on average links. What's E here? The number of exit gateways. Oh man, up to 20, eh? Okay. And N1 and N2 is a link between the nodes indexed N1 and 2. And then, oh, okay, that's as, of course, yeah. That's dependent on this stuff here. Okay, so we're just about ready to start solving this thing. Los Angeles 2029, Resistance HQ, review of facts. Last Saturday, hundreds of brave fighters risked their lives to destroy Skynet. Stop. Using contaminated moto terminators, they managed to inoculate a lethal virus to Skynet. Stop. Problem. Skynet is fighting back. Stop. John, once more, we need your help. Stop. So apparently, we're John. And we are tasked with, oh, cool. Is this thing going to play out in there as we, let's see. Yeah. Oh, that's neat. Game information block. The agent is at position 1. Standard output 0, 1, which is just okay. Failure, agent has reached. Link 0, 1 severed. Agent moved from 1 to 2. Huh. Very interesting. Okay. Game information, action, output, debug. Okay. All right. So let's think about this. My whole setup here. I'm ready to start coding. We're definitely going to need some sort of a graph, and we're going to need to implement, I'm thinking, well, let's see. The Skynet agent is moving around the graph trying to get to a gateway. And we need to prevent it from getting there by basically deleting links between nodes, one at a time, one per turn. So the algorithm we need to write is basically an algorithm that will determine the best link to sever this turnaround in order to prevent the Skynet user, Skynet agent, from getting to the gateway. So it's basically a pathfinding algorithm. So we can use like breadth first search for that, or let's see, yep. That would go through the all of the nodes. Well, at least until we find, okay, wait. Would we start from Skynet? Yes, that's what we would have to do. Okay, so we would have to start from Skynet's node, Skynet agent's node. We'll call it the agent going forward. So we start from the agent's node, and we propagate outwards through the graph until we hit a gateway. And then, okay, and we need to store, at the same time we need to store, a value. Yeah, so this really is like a pathfinding. So we use breadth first search, but I think we need to implement like a, well, not a star, but maybe like, what's it called? Dijkstra or whatever it's called, algorithm. I can't remember how that works though. Well, it's basically breadth first search from what I remember, breadth first search, but you kind of store as you go along through each node. You store the cumulative value, basically like the weight, the cumulative weight of each link. And in this case, our links don't really have a, they don't vary in difficulty or length or anything like that. They're just valued 1 each time. So it's basically you store each time the amount of jumps. Would that make sense? No, I don't think you would even need to do that. You just need to store the previous node you're coming from. because we're going always one step outwards each time. So all you need is a queue. Yeah, okay. Enough of enough of mind coding. Let's put something on the screen. Let's see. So we're gonna call this. Well, first we should implement a graph, I guess. All right. So let's just call that a graph. And make a class that we're gonna call graph. What's going to be in that graph? What is it? Well, it's going to be an array, right? So a private array. Let's just call it array for now, and we can just initialize it. But I want to know what we're going to type. So what's our input again? We're getting here, right? So we're just getting node numbers. Each node is numbered. So okay, our index here in this array can be simply the node number, and then each index will contain an array of connected node numbers. That's pretty much the most basic, I think, implementation of a graph. What do they call that? Adjacency list or something like that? Yeah, I think that's what it's called. As opposed to an adjacency matrix, which is a different way to represent a graph, but I don't really remember how it works, so let's go with this. So, okay. So it's an array. We know that. It's an array of what? Well, numbers, really? No, it's an array of numbers. Yeah. But we're probably going to need something a bit more clever than that. Do we need to... Okay, let's start with that. Let's start with that. It's pretty simple. Do we need a constructor? How are we going to build this thing? Stuff is coming in as a series of links. So they don't actually give us... They don't actually give us the... Maybe I should just copy this, or maybe this here. No, that's fine. They give us, okay, we get the amount of nodes. We know the amount of nodes, so we can, right off the bat, create our array, our graph. Yeah. What are they saying here? What do they have going here? And the total amount of nodes, and then we're not actually using that anywhere else after that, are we? No, we're using the amount of links. We're iterating through the links. Okay, but still, this can be useful to create our array. So we'll construct our graph. Constructor will take in a number which will be number of nodes. Yep, I don't really need to store that. It's just for the constructor. And then in the constructor, so we won't initialize that here. Instead, what we'll do is okay, we can't call this array. Well, we could. I mean, there's nothing wrong with that. The other option is to call it graph. Nah, nodes. Oh yeah, it's a list of nodes. So nodes. There you go. And now we create our nodes array by doing new array. And then we pass in the number, right? Array length. Correct. Which will be our number of nodes. I just need to store that though into nodes like that. Okay, so we've got the first step to creating our graph. Now we need to do something with number of links, number of exit gateways. Oh. How? Yeah, we're going to need to check each node to see if it's got a gateway. So does that mean that I need to implement each node as an object, since I need to store that information? Do I need to store that information inside the nodes themselves? I could probably make a simple check. Okay, I'll leave that till later. I think I could get away with not doing it. We'll see. So the next step would be to populate our nodes with the connecting nodes. N1 and N2 defines a link between these nodes. So basically N1, 2. So maybe I could just, I guess I have two options here. In my main, accumulate this information and then pass it as a parameter to the constructor, or just, no, you know what? No, I'll implement a function for that. So it'll be a public one, and it's going to be called add link. Add link, and it's going to take node 1, which will be a simple number, and it's going to take node 2, another number, and what do we do with this? We simply take this node, look up node 1, and then yeah, I need each of my node indexes in that array, in the nodes array, to be an array itself, an array. So is there a way to initialize the, let's take a look here at, let's see, I have this somewhere now. An array. I think there's array.fill, which will fill up the array with whatever value you want, but I'm wondering if I can just do that when I actually create it. Array.of. No, that's not what I want. Array.from. From an array like array.repl. No, array.fill is what I was thinking about. So modifies all the elements of an array from start index to an end index with a static value. So I could just pass in an empty array. I think that would work. Let's see, what other ways do we have to create an array? Oh, I know. This, and since we don't care about performance or any of that stuff, well, I guess array.fill would do the exact same thing, but here's what we could do. So new array number of nodes. So we've got an array here. And then, actually, I think I don't even need the new, right? Let's just check here. Array, boom. Syntax, new array, array length, accessing array elements, array. Nope. Well, yeah, I don't know why, but I think I remember I don't actually need the new. But it might not be a bad idea to do it anyways. So, but if I do it that way, yeah, so let's try it like that. And it's not complaining too, so if I do this, see, array constructor, array length, there we go, yeah. Okay. Then I'm going to unpack this array into the array here, and then I'm just going to use map. Although fill would do the same thing, right? Fill with an empty array. No one's complaining, so this seems to be working. Should, anyways. All right, so now that we know that we've got our array of arrays, we can simply do this.nodes, index of node 1, and then just push node 2 in there. Simple as that. We're going to need a way to remove links. So remove link node 1 number node 2 number. Oh, wait a minute. It's a, what do you call that? A bidirectional graph, right? They're not saying anything about it being unidirectional. So logically, and how are we being fed that information again? I think that, so if node 0 is connected to node 1, yeah, we're only seeing node 1 connected to node 3, so there's no duplication, but technically, if 0 goes to 1, 1 also goes to 0. I don't believe there was anything said about it being a one direction graph. So we'll take for granted that it's bidirectional. So I need to make sure that I'm syncing. So as I'm adding this node here, I need to make sure that I'm also doing the exact opposite, which now I'm starting to wonder if this is the easiest implementation. It's not that complicated, really. because the other option would be to have the nodes could be objects, and on the nodes I could have a a property that would be called connectors or something, or links, and links could be themselves their own objects. Let's keep going with the implementation we have. This still seems a little simpler, and I think we won't need more complicated than that. So nodes dot node 1, and then I need to find the is there something like find and remove? Filter would work. Filter function that accepts up to returns the element of an array that meets the condition. Oh, but it doesn't remove it from it, so that's no good. Concat for each copy within entries, every filter find index includes index of keys, last index of map, pop, reduce, right, reverse, shift, slice, returns sum, sort, splice, which we could use once we get the index. Values, yep, so that's what we're going to need to do. We're going to need to find, returns the value of the first element in the array where predicate is true, and define it, no. Find index, returns the index of the first element in the array where predicate is true. But we need to pass in, isn't there a simple index of, returns the first occurrence of a value in an array. Okay, good. Index of allows us to search without having to pass in a callback, basically. So nodes index of is well, node 2, right? And once we have that, we can just do this dot nodes, boom, dot slice. Ugh, no, that's ugly. Can't do it that way. So let's make a temporary variable, and we'll call it, what are we going to call it? Node 1. Node 2's index in node 1. I don't like it. How about we call it temp for now, until something comes to mind. So this dot nodes, and we take node 1 and we splice it. Okay, start. So that would be our index, and our delete count is just 1. Alright, so what do we call this thing? How about we call it index. Node 1 link index. Yeah, let's go with that. And basically do the same thing here. Const node 2 link index equals this dot nodes bracket, oops, what is it? Yeah, node 1, So this is wrong. No, this is, okay, node 2 here, and this is node 1, and then this will be node 2, index node 2, link index. We just delete the 1, and that would effectively remove the link from our graph. Anything else we need to implement? At first, anyways. We need to store, oh, we need to maybe find a place. Should we put that in the graph? The index of the gateway. Okay, well, for now, let's just make sure that we're building our graph properly. So we would be, okay, we can remove this. We can also remove that. We'll keep the rest for now. Number of links, so we need, no, number of n. This needs to be here. Okay. And the total number of nodes in the level. So once we have that, we can create our graph. So const graph. Let's call it network. Network is equal to new. Oh, I need to export that. New graph. Graph. And it needs to take in our n. Okay, so good. We've got our graph. Now we, okay, we need this here. So new, not new. So we take our network dot add link. Node 1 is n1 and node 2 is n2. And that should populate our graph. Now if I am to, let's try this. Once we are, I don't even care about that. I just want to, once we're done with this here, let's say, console error. Let's get our, if I just pass in network, let's see how it's going to output this. Curious to see that. Okay, try again. All right, okay, cool. Cool. I just want to see the error stream. Thank you. So, oh, but I don't even know what the input is, do I? 2101, 2101, 2101. So I don't know, something is probably not quite right. If I go output stream, no. If I go this here, okay, let's find a way to, we'll log this console.log or error, and just the actual inputs. Okay. that. Then okay, so 1 is connected to 2, and 1 is also connected to 0. So this is index 0. It is connected to 1. It shouldn't be connected to 2. And this is indexed 1. There shouldn't be 3 indexes. Why is there 3? What? What did we do? We're going to have to use a bunch of console log stuff here because I said so. How's that? I'm the boss. See what that looks like. Okay, interesting. So it's creating 3, 0, 1, and 2. Oh no, there are 3. Okay. I was right. I was missing the 2 there. So 1 or 0 is connected to 1. That's the only thing we have here. So in 0 there should be just 1. So we know this is good. Let's take a look at this here. So we're pushing what am I logging? I'm logging the actual node array. Okay. One, 2. What am I getting here? 1, 0. Okay, yeah, that's the actual input coming in from okay. So once we got 1, 2, we're storing that. We're storing 2, 1 in every single slot in our array. It doesn't make any sense now, does it? This node's that. Node 1, push node 2. What is this? Defines a link between these nodes. And 1 is 1 and 2 is 2. Yeah. And then we're shoving that everywhere. Okay, I'm obviously doing something wrong here. this nodes. Node 1. Dot push node 2. What if I was just looking here? I'm putting 2 in each one. What is going on? What the heck? For each link, yeah. I really don't understand what's going on. Oh, I'm going to have to kind of implement this on my side, I think, and debug this. Unless, what else could I try here? Well, I could do, okay, let's try this quickly. This might save us. So, new graph with 3, I think it was. Let's graph. So right there, let's take a look at this here. Right, so nodes is an array of arrays, and there's 3 of them, and they're empty, so that's good. That's what we want. Now let's say I wanted to, let's just do this, it'll always update that way. Let's say I wanted to do graph dot add link, and then simply 0 and 1. What? What the heck? What am I not seeing? Push node 2. Alright. What is this here? It's an array. It's our node 1 array. Right? It's the same as if I was doing, in this case, 0. Right. Now I'm pushing a number. What is that number? Number is 1. That's right. does it end up in every single slot in my array? Wow, I feel so dumb. There's obviously something I'm not getting here. It should be pushing to this here. It should be pushing 1, but only to this array here. That is some weird stuff, man. Does it have something to do with the way I'm... Oh, that's exactly what it is. Of course. Of course, of course, of course. Wow, okay. Well, I just learned something. Let's see, this is what's happening. Fill is actually putting the same array in each. So I will use a map. Okay, wow, that was interesting. That was interesting. So map x, just that. Boom. Okay, guess that didn't work. Map value any index number. Right, because they're empty right now, but so x is fine. Return this. Same thing. Why is that not working? If I was to do 1, what would I end up with? If we just forget this for now. That's interesting. You're not making this easy. If I get rid of this altogether. Right. I've got an empty array, and I'm saying, why don't we map this? And then, maybe because there's an empty value. Should work though. Why wouldn't it work? That would make it a string of 1. No, it just doesn't want to. Just doesn't want to do it. So if I just do for each, maybe. I'll probably have the same problem. error. That is frustrating. So, different way to do this then. Still gonna make our new array. With our number of nodes. Well, I guess we might as well just do a for loop like that, maybe. 0 I is smaller than number of nodes. And then just this dot nodes I equals that. Okay, and now if we try this, there we go. Okay, I don't like this though. There must be a better way to initialize this. Don't understand why map doesn't work. Anyways. So let's keep going with that. Stop cold off. Don't need this anymore. And let's run this. Okay, so N1 is connected to N2, so 1 is connected to 2, and 2 is connected to 1. Now N1 is connected to 0, so 1, 0, 0 is connected to 1 here, and 1 is connected to 0. So that works. That is working. And good. I think we can keep going and try to implement our search algorithm. Okay, so what do we need to do here? We need to start at the agents. Where do we get the agents? The node on which the Skynet agent is positioned this turn. SI. So this is where this is happening. So we basically need to run that search algorithm every game turn because the network changes, right? Because we remove a link and because the agent is no longer in the same place. Right. I mean, if we really wanted to optimize the thing, there's probably a way to cache some of, well, I don't know, whatever, but I don't think we need to do this. Okay. Let's call it, what are we trying to do here? We're trying to find best link to remove. That's basically what we're doing. Find best link to remove. And that link is going to be expressed simply by a tuple. How do you do that in TypeScript? Oh, I think that's the way you do it. I think. So if I was to return, let's say, 1 in a string, it would say this string is not assignable to type number. That's correct. If I was to do 1, 1, we're good. If I was to do 1, 1, 3, type number, number, number is not assignable to type number, number. Good. And if I was to do just 1, same thing. Good stuff. Okay. What I've got here. Don't need you, thank you. End. So we've got the proper return type. What do we do? We need to implement our breadth first search algorithm. Okay, so we need to start our search at the agents node, which is this number. Okay, what do we do with that? Let me see. I think I can. Okay, yeah, this is good. Let's see. Okay, let me fold that over here for your benefit. Graphs, but I think this is all right. Breadth first, yeah. Breadth first. Pass in the node. Q in Q node. Mark node. While Q is not empty, process Q dot front for so we're putting our root node basically in the queue. We mark that node as being processed or something like that. Then we start the loop. We get a node out of the queue, which, at the beginning is our root node. Then we process Q.front. Process Q. While Q is not empty. Okay. Yeah. While Q is not empty, then we process Q.front. So we take that node and we do whatever we need to do with it. And then, once we're done doing whatever we need to do with it, and for us, process will probably just be checking to see if we are, oh no. I do need a way to store Okay, let's think about this here. I don't think we'll be able to use just simple numbers for our links, because we need to store some information in there. Although we don't want to persist that information. So maybe I could just make another data, like another object. Okay, let's keep thinking about this. So now we're done. If marked child, if not marked child. So for each child of Q.front. Okay, that's like peak, I think. Right, because this is DQ here, which is fine. We can just use a an array for that in JavaScript. We don't really need to implement a queue. I don't think so. If not marked child, q and q, marked child, and the if statement, and the for loop, take that thing off the queue, and then boom, take the next one, which would be one of the child, and then until there's nothing left in the queue. Okay, not that complicated. Once you wrap your head around it, I think we can do that. So we've got our starting node. We need to mark that node. So how do we do that? So we're going to need some kind of data structure. If we need to mark the node, and we need to know where we're coming from. Okay. So let's see, what would that look like? What's the information do we need? So marked would be a simple Boolean, right? Boolean, not Boolean literature. I don't know what that was, but and so okay, let's say we're initializing the first one here. I'm not gonna do a type really. I think we're only going to need 2 properties anyway, so let's not make this more complicated than it needs to be for now. So marked false. So we're starting off, we're not marked, right? What else do we need to know? We need to know precursor. Starts off with null. So let's call this node, or maybe node, yeah, we'll call it node for now. Okay. And what do we do with this? We mark the node. That's the first thing we do. So well, if it's the first thing we do, then let's make it true. Precursor, there's no precursor because we're the root node. Now, what do? We've got a while statement. Got a while statement. Oh no, I missed a step. It was Q and Q. Okay, yeah, we shove that in. We shove that in the queue. That's the first thing we need to do. So we need, we're going to call that queue. When really we're just going to use an array, but and it's a queue of of this stuff here. No, I don't like this. We should probably let's see. Oh, here we go. Simple as that. Boom. That's our first thing in the queue. Okay. While. And this should type our queue properly at the same time. Yes. While queue dot length is bigger than 0. What do? we process the thing that's, okay, hold on. If we're going to do a queue, queue is first in, first out. Right? Just like when you're queuing in line for, you know, to go into the theater or whatever. So first in, first out. How do we, okay, so we need to basically use shift to get stuff out and just push to get stuff in. So push, push at the end, shift at the beginning, which is not a very performant way to remove stuff from an array, but I don't think performance is going to be a problem here. So our peak is just going to be looking at the index 0. So we're going to call this, well, for now, let's call it this, the process. Well, actually, no, I'll extract it later. I'll just do process. What's that? Process node at index 0. I'll figure out what that is later. And once we're done with that, we then for each child of q.front. Yes, so let's see. Oh, I guess we do need more information than that, don't we? We need to know the node, which is agents node. I wasn't even using it. Agents node. Okay, that then allows us to do this dot nodes and agents node. Okay, then for each child node, what do we do? For each child node, we first check if they are marked. How would I know that? Because I sure am not storing that kind of stuff in here. Okay, yeah, that's not going to work. I'm going to need to actually store the stuff. But then if I store it in my actual graph, that means I need to, every turn I need to erase this information. Don't like it at all. At all. Unless I mirror let's think about this here. I've got my child nodes, but I need to check if they have been marked. In other words, I need to check if they are in the queue first. Right, because since it's not a tree but a graph, it is possible that we will end up in the same place, but you know, coming from a different node. So how would I go about checking that? I would need to go through the queue, find the child node. No, that doesn't seem like a good idea at all. All right, the other option is to actually construct like a real graph using actual nodes with connections to other nodes. Basically a linked list graph, something a bit more sophisticated than what I'm doing here, but this can serve to create the thing I need here, and I could just throw all of that away afterwards instead of having to go and erase, you know, the marked and the precursor and all that stuff. Although this shouldn't change, but it could. Okay, what would that look like? Let's just forget about this for now. Let's say we were to wait a minute, there might be a way not to. If I was to so the thing I'm trying to avoid here is to have to iterate through the queue to find the particular child node. Would that be so horrible? We have said that there is a maximum of 500 nodes. So I mean, I don't think it's going to oh yeah, let's just do it. Let's just do it. Okay, so we do queue dot find. Let me just get rid of this. Q.find will return the actual value, I believe. Returns the value of the first element in the array where predicate is true. Yes, thank you. And we are looking for, that's our node. Looking for a node dot node. Yeah. Let's call this something else. Value, maybe. Entry. Let's call it an entry. Entry dot node is equal to child node. Okay. So if it finds it, it returns it. Otherwise, it'll return undefined, right? So const, what are we going to call this? Entry. No. Found. I don't know. For now. And what do we we do with this? So if I do have one, because I might not have one. Okay, so if I don't have one, I simply if not marked child, Q and Q child, and mark child. If it is marked, it shouldn't be in the queue, is what I am to understand. Huh, so that's not going to work. No, I really do need to implement an actual graph with all the stuff I went a little overboard here. So we're going to, well, then it feels kind of silly to create a graph inside a graph, you know what I mean? Like, so maybe we should just go ahead and implement the real deal. Well, this is fine here. What we really need is to have a way to have our nodes be objects. Right. Mm-hmm. Okay. So we'll make a node class. Well, let's call it graph node because node is probably something else in the global. Well, maybe not. Maybe not. Okay. Class node. What do we need? We need, oh, I removed it, but anyways. We need a link to so we need precursor, which is going to be a number, or do I need to actually link a okay, let's leave that. Let's build that as we are doing this. The first thing we were doing was to enqueue the node. So the agents node we're passing here is just a number that we're getting from somewhere else. Anyways, for now. So let's do, okay, we're still going to need our queue here. So const queue is equal to this thing is going to be an array of nodes. And now we actually we do what? We do this. No, we do queue that push. And oh, actually, for the first one, I can just do this. This dot nodes, and then agents node. Okay. All right. Then need to mark that node. So this dot nodes, agents node, dot mark. And this will be a mark. Boom. It's basically a setter. Right. It's going to this dot marked equals true. And this, let's see, marked. That's private. Private marked is equal to false. That's the default. Okay. Seems to be the problem here. Oh yes, because we are not putting the right things in there. So it's going to be a node of node objects. So that's all different. So we don't need arrays anymore in here. But this we do need. Okay, and then we need to actually create a new node. New node that takes in the number of our, so we need a constructor that's going to take in the linked node, and that's just going to be a number. And then we so we need an array of child nodes, or let's just call it connected nodes. It's not really a tree, right? So I don't know if it's, well, whatever. Child nodes is going to be an array of nodes that will initialize right away, and then we just come in here and go this connected nodes dot push, and we're pushing nope. We just want that to be, do we want this to be the actual node? Or do we want this to be just the index to the node? Let's make it be just the index for now. Push dot linked node. Okay. So then when I'm constructing nodes in a nodes array, okay. So I'm pushing node 1 push. Does not exist on type node. Right. Because what I need is to actually the opposite here. I'm not doing this right. So equals a new node, right? Nope, not necessarily. Okay, this complicates things a little bit. Maybe I should just create all the nodes up front. Let's get back here for now. Yeah, that would be probably better. Less confusion. So let's forget about this. Let's forget about that. Instead, we will. Well, then we've got like 2 layers of add links, but I don't care. Well, actually, here what we're doing is we're adding a connected node. Add connected node. That's what we're doing. It's not returning anything. Okay. So what are we doing? We need a node number in here, so connected node. It's just a number. And we just push that number to connected nodes. And no, not number. What am I saying? Connected node. It's connected nodes. Forgot to push. Push. Okay. So then we're doing this. Then we're doing add connected node. And we're doing the same thing here. Add connected node. Okay. Then it'll be the same process when we want to remove one. So remove connected node, connected node. Number this dot connected node. What I was doing? Oh yeah, I need to do this in 2 steps. I need to find it in the index, and so let's go like this. So node 1 link index. So let's just call it node index. This dot connected nodes. Index of connected node. Then once we've got that, we can splice from our connected nodes the node index. There we go. And now here, all we need to do is call remove link. So what am I doing? Not waiting to do this dot nodes from node 1. And then dot remove connect node, node 2, and essentially the same thing here in reverse. Node 2 and node 1. Okay, now, we got rid of all the errors in here. We can keep going. So this node's that agents node, we mark it. Boom, that's done. Now what? Then we go into our while loop. While q is not empty, so q dot length. Actually, I don't even need to do is bigger than 0. Just doing q dot length will work. While q dot length. And then we process node at index 0 in the queue, and then once we're done with that, that's what we were doing. Once we're done with the data for each child, right? So I do q at 0, and that gives me access to my node. Where do I want connected nodes to be open, public like that? I do not. I do not want that. So I've got, let's call this, let's make a getter for that thing. We'll call that get connected nodes. And we will return a, I don't want to just return this connected nodes because that's just, then they get to change, play around with it. So the best thing would be to return an iterable. What's a good way to do this? Connected nodes dot values returns an iterable of values in the array. Now that is what I want to do. It's the type of this thing. Return iterable iterator number q dot get connect nodes. Whoa. Get connected nodes dot, oh right, then I can just do for node of this should work. Why doesn't it work? is not an array type or a string type. Okay, and so what? Shouldn't I be able to do this? In, maybe? Oh, okay. Interesting. What is that going to give me? I am curious to see. So for that I need to create a graph. Const graph equals new graph of 3, yay, and then graph dot add link. What'd that look like? Yeah, graph dot add link. Node 1 and 2 are connected. Cannot read property add connected node of undefined, so right, because we don't have that many. 0 and 1. We're still getting that though. Interesting. Interesting. The problem is here. Cannot read property add connected node of undefined. So he's saying that at nodes, node 1, there's nothing. Right, because I'm still not creating my nodes. I was forgetting about that. So for let I equals number of nodes, I is smaller, no, is equals 0, I is smaller than number of nodes, and I plus plus. Okay, then we simply do this dot nodes of I is equal to a new node. There we go. And that should take care of that. There we go. Good. And now if we look at our graph, that's right. We have 1, 2, 3 nodes, 2 of which have connected nodes, index 0 and 1. Okay. Now, what was it I wanted to try? Find best link to remove. Yeah. I was just curious about this thing here, so graph, and let's add another link. Add link between 0, 1 and 2, let's say. Okay. And then graph dot find best link to remove, start at index 0. Cannot read property mark of undefined. Okay, no, that was just a... What are you? getting to this here? Is that what's going on? I guess we're not. What are we doing here? We're calling it with 0. We're queuing this dot nodes 0. Then we're marking it. Then so maybe we should do this then. That didn't change anything. Oh, I know what's going on. We are stuck in an infinite loop. That is what's going on. This should fix our problem. So all this, do that for, I just want to see this here. It really looks like we're not getting there. Bigger than 0. Node is a string. It shouldn't be a string. What are we doing here? Am I even getting to this part here? Yo. Yeah, we are. What are we getting here? It's like we're not. If I do of, then it's not working. If I do in, I get something, but iterable iterators. Actually, if I just look, I was in the array, I think. If we just look at values, which is what I'm returning. Yeah, I should be able to do that of iterator. Why doesn't it work? Const node of, and why is an array type, is not an array type or a string. What am I doing here? Get connected nodes. I'm returning values. Okay, that's what I'm doing wrong. Use compiler option, down level iteration to allow iterating of iterators. Well, yeah. Why wouldn't I want that? Why would I not want that? Down level iterators. Where do I find this? It's not in there. Let's add it. Down level iteration. Please. Thank you. Hey man. Hold on. I am on day 38, I think. Sounds about right. Thanks, man. Are you doing the 100-day challenge as well? Am I new to this? I am new to the 100-day challenge. It's the first time I do it. Am I new to coding? No, I'm not. I've been doing it kind of part-time for about almost 3 years now. I have zero coding experience except for basic back in the early 80s. Oh wow, that's funny because that was the same with me. When I was about 8 years old, so that would put us at around 1988, my dad bought a Tandy 2000, so that was a 286, and it came with basic, and you know, I fooled around with that a little bit. I got like a few books where you would have like the like make your own adventure game, and it would have like the entire code listing. You would just have to transcribe it into basic and then it would work, you know. So I played a little bit with that when I was younger, but then I was always into computers and stuff, but never got into coding until a few years ago. Okay, so that should work. Good. No, it's not bugging us anymore. But I'm still not reaching this here. And I'm wondering if that's because Quokka is doesn't know how to deal with this. Maybe if I stop and start it again, since I changed the compiling. Aha! See? Okay. Good. Good, good, good. And we're getting, what are we getting? We're getting 1. Because there's only one connection. But let's say we were creating a much bigger graph. Much bigger, well, you know, slightly bigger. And we were adding, actually that's all I needed to do. There you go. So this works. So far, so good. I can remove this. I'm a network engineer by trade, but looking to learn. Cool. That's nice. So, is there a language in particular you're thinking of learning? Okay, so for each child of Q dot front. All right, now I need to check if it's marked. So if I did one of those web dev courses online a couple of years ago, but looking into Python now for creating scripts for network management and troubleshooting monitoring. Yeah, right on. Python's I like it. I've played with Python a little bit. You could use Python for that. You can also use JavaScript. With Node, it runs on the back end, it runs on the computer. It's not just for web development. Okay. Right now, I'm using TypeScript, which is a superset of JavaScript. It's basically JavaScript with typings. What am I checking for here? That the child is not marked. So I would have to go this dot nodes. And then I would I would do node, right? Node. And then basically I need is marked. Return this dot marked. So if this node dot is marked, now I want to check that it's not marked. So I want it to be false. If it's not marked, I'm putting it in the queue. So queue dot push. In the queue, I'm actually putting the nodes in there. So this dot nodes node. So maybe node index instead. Yeah, okay. So anyways, when it's slow here at work, I jump on Twitch, YouTube, and just scroll through folks' coding to try to gain better understanding of the logic, if that makes sense. Yeah, totally. You're not the only one that does that. I do it too. A bunch of people do it. It's kind of weird, when you think about it, just watching other people code, but you do learn a lot by doing that. It's amazing how, like, there's many different ways to do the same thing, and everybody's got their own little twists and tips and things that they do, and you're like, what? I didn't know you could do that, or I never thought of doing this that way. So it's pretty cool. Okay, cue that push. Then once I'm done with the pushing, I mark this dot nodes node index. Okay, this is crazy. I'm doing this like 15 times in here, so let's just get it right here. We're going to call it this nodes node index. We're going to call this const connected node equals this dot nodes. Perfect. Now if connected node is marked, queue the push dot connected node, and then connected node dot mark. Okay. And we're done with the if, we're done with the for loop. I can get rid of this. Actually, get rid of this. the only thing I've left to do here is to remove the node we're processing from the queue, which would be a shift. Remove the first element from an array and returns it. I don't care to do anything with it, I just want it to be removed. And then we're done, and it would go like that until we are completely done with the traversing the entire graph. Cool. All right, that puts me at the 2-hour mark, and that's going to be it for me. So beep it, 1237. It was a pleasure to meet you. Hope to see you again. I'm usually streaming every weekday in the morning, 9 Eastern Time, North America, except for Fridays, where I do it in the afternoon, starting at 1:30. So maybe we'll cross paths again. You're Central? Okay, cool. So that's not too bad. That is not too bad. All right. If you have any questions or need any help with your coding career or endeavors, just let me know. I'll be happy to help. Yep. You have a good weekend too. Take care.